Welcome back again to this new Learning Explainer. Today, we're diving into a massive topic in modern software. How do we build applications that can actually handle the pressure? Ones that don't fall apart when things get busy. We're going to explore how to leave those fragile, all-in-one systems behind and build something truly resilient and scalable, the AWS way. Let's get right into it. So, does this sound familiar? You need to make one tiny change to a feature, but you're secretly terrified it's going to topple something completely unrelated on the other side of the app. Yeah, that feeling? That's the classic sign of a tightly coupled system. It's when development slows to a crawl, and trying to scale up for more users feels like an absolute nightmare, because every single piece is chained to every other piece. Well, the solution to this whole mess is a concept called decoupling. The big idea here is to break your application up into smaller, independent services. Now, these services can still talk to each other, but, and this is the key, they aren't directly dependent on one another. So if one little service has a problem or goes down, it doesn't bring the entire system crashing down with it. Okay, so that sounds great in theory, but how do we actually do this in the real world? Well, this is where AWS comes in. They give us an incredible set of services that are basically a specialized toolbox designed specifically for building these kinds of decoupled systems. So let's pop open that toolbox and see what we've got to work with. First up, we've got Amazon SQS, or Simple Queue Service. The easiest way to think about SQS is as a buffer, like a digital waiting line for tasks. One service, which we call the producer, can drop a message, think of it like a work order, into this queue. Then later on, another service, the consumer, can come along, pick up that message, and process it whenever it's ready. This is amazing for preventing that consumer service from getting totally overwhelmed by a sudden flood of requests. This makes SQS absolutely perfect for any task that doesn't need to happen right this second. Think about processing a new customer order, or transcoding a huge video file, or just kicking off a complicated job for another microservice. The service that sends the request doesn't have to wait around. It just drops the message in the queue and moves on with its life. Next up in our toolbox is Amazon SNS, the simple notification service. Now, if SQS is a one-by-one waiting line, think of SNS as a megaphone. A single event happens, and bam, SNS broadcasts that message out to many different subscribers all at the same time. And those subscribers can be pretty much anything: other SQS queues, Lambda functions, or even things like email addresses and text messages. This is just incredibly powerful for what we call fan-out patterns. So imagine a user uploads a new profile picture. You can publish one single message to an SNS topic. That one message can then trigger a Lambda function to create thumbnails, send a message to an SQS queue to run a content check, and notify another service to log the event. It's one event triggering many different independent actions. So let's just put these two side by side, because this is where folks can get tripped up. SQS is a pull model. A worker has to actively reach out and pull a message from the queue. It's a one-to-one deal. SNS, on the other hand, is a push model. It actively pushes the one message out to its many subscribers. So bottom line, SQS is for managing a workload, SNS is for broadcasting an event. But what if you need to react to events that happen outside of your own application? Well, that brings us to our next tool, Amazon Event Bridge. Think of Event Bridge as the central nervous system for your entire architecture. It's a serverless event bus that can listen for events not just from your own code, but also from other AWS services and, this is huge, even third-party partners like Stripe or Zendesk.
Honestly, this is a total game changer for integration. Instead of writing all this fragile custom code to connect everything, you just send events to the bus. Then, EventBridge uses simple rules that you define to intelligently route those events to the right places. So, for example, a new ticket created in Zendesk could automatically trigger a Lambda function right inside your AWS account. All of that with just configuration, not a single line of custom integration code.
Okay, so we've got all these messages and events flying around our system, but what actually does anything with them? What does the work? Well, that's where AWS Lambda comes in. Lambda is what we call serverless compute. It lets you run small, focused bits of code in response to a trigger, like a new message in a queue or an event on the bus, and you never have to think about servers. Not once. You can really see its power as the connective glue here. A new file gets uploaded to an S3 bucket, and a Lambda function can trigger automatically to process it. A new user signs up through your API, a Lambda can handle all the backend logic. It really is the action part of this whole event-driven equation. Now, how do our users or our mobile apps actually talk to this cool decoupled backend we're building? They need a way in, right? They use the front door, Amazon API Gateway. It sits right in front of all your backend services, like your Lambda functions, and gives the outside world a clean, unified API to talk to. It completely decouples your clients from the messy internal details of your architecture. An API gateway is absolutely essential because it handles all the boring but critical stuff for you. It can manage authentication, authorize requests, it can throttle traffic to stop people from abusing your API, and it can route requests to the correct backend microservice, all before your own code even has to run. Okay, SQS and SNS are fantastic for individual events. But what if you're not dealing with single messages, but a massive, continuous stream of data, like a fire hose of information? I'm talking about IoT sensor data, application logs, website click streams. For that kind of fire hose, you need a different tool, Amazon Kinesis or its managed Kafka sibling, MSK. What this does is it decouples the things producing the data from the things consuming it. You could have thousands of IoT devices all sending telemetry data into a stream without ever needing to know what's on the other end analyzing it. This is how you build things like live, real-time analytics dashboards or complex log analysis pipelines that can handle just an enormous amount of data. So far, we've mostly talked about a single event triggering a single action. But a lot of times, a real business process is a whole sequence of steps with some pretty complex logic, right? Like process the payment, then update the inventory. And if that works, send a shipping notification. Trying to code all that logic inside a single Lambda function, well, it gets messy fast. And this is exactly where AWS step functions shines. What's so crucial here is that step functions manages the state, the error handling, and the retries for you. So if that update inventory step fails, step functions can automatically retry it, or it can branch off to a special error handling path. It keeps all of that complex coordination logic completely separate from your individual functions, which is just fantastic. Okay, that was a lot. We've looked at a bunch of individual tools, so how do they all actually fit together to build something real? Let's walk through a classic example of what a decoupled request flow looks like in the wild. Okay, follow me on this. First, a user's request comes in and hits our front door at the API gateway. That gateway triggers a really lightweight Lambda function whose only job is to put a message into an SQS queue and then immediately send a success response back to the user. So the user isn't stuck waiting. Meanwhile, in the background, a completely separate worker service picks up that message and does all the heavy lifting. When it's done, it saves the result to a database, which in turn triggers an SNS notification to send an alert. See? Every single step is totally independent. Now, I know that example might seem a little more complicated than just having one big application do everything, but trust me, the payoff is absolutely enormous. So let's just spell out exactly what you gain by building things this way. The benefits are just so clear. You get incredible scalability, because if you get a flood of requests, you only need to scale up the worker service, not the entire application. You get amazing fault tolerance. If that worker fails for some reason, the messages just stay safely in the SQS queue, ready to be processed later. The user never even sees an error. You get flexibility, because you can change or upgrade any single piece without a massive, scary rewrite. And with serverless tools like Lambda, you get huge cost savings, because you are literally only paying for compute when your code is actually running. And that really brings us to the final and most important question. This isn't an all-or-nothing deal. You can, and you should, start small. So take a look at your own applications. Is there a really slow, resource-heavy process that you could offload to an SQS queue? Is there a notification system that could be rebuilt with SNS? It's worth asking, which part of your stack will you decouple first? And that is a quick tour of the AWS decoupling toolbox. Thanks so much for watching. I would really love to hear from you. What are some of your favorite decoupling patterns or tools that you use? Let all of us know down in the comment box. And hey, if you found this useful, please consider subscribing for more explainers just like this one. We'll see you in the next one.